So the mean value theorem, like many theorems, and you've heard me say this before, and I'm probably going to say it again throughout this course, the mean value theorem, like many theorems, is fairly straightforward to understand. In concept, it's actually a pretty approachable theorem to break down and understand what exactly it's trying to say. But its implications are incredibly important, and we're going to see it pop up time and time again as justification for why certain other theorems or concepts work in calculus. If anything else, just basically understand that the mean value theorem's job is to compare the slope of a secant line through 2 points on a function to the tangent line between the points. That is to say, previously we talked about the average rate of change versus the instantaneous rate of change. And the mean value theorem is a way of connecting these two concepts. In short, what the mean value theorem is saying is that if a function is continuous on the closed interval AB and differentiable on the open interval, there will be at least one x value, which we'll call c, such that the derivative is equal to the average rate of change. Or there will be at least 1 point, some x value within that interval, such that the slope of your tangent line is exactly equal to the slope of the secant line. And if you want to kind of take away or strip away the idea of slopes and tangent lines and all that, it's just basically saying that whatever the average rate of change is between 2 points on an interval, there has to be some point in that interval where the rate of change in that moment is equal to your average rate of change. And I know that still sounds like a lot, but let's do a quick exploration and we'll see if we can break this down a little bit further. So take a moment right now, pause the video, and for each of these graphs, see if you can sketch one tangent line. And in certain cases, you can do more than one, so try to do as many as you can, where the tangent line is approximately parallel to the given secant line that you see here, kind of in that dotted line between the two endpoints. And if a tangent line is not possible, kind of think about why you think it's not possible. So as we go through this, let me just kind of break down, let me do this in a different color, a couple of different possible tangent lines. And I'm just doing some rough sketches right here. I'm just going to kind of see a point where it looks like I think I can sketch a tangent line that looks like it's about parallel to the secant line that we see there, somewhere around there. Now, for the next one, initially I would think that I would be able to sketch a tangent line somewhere around here, right? That's not great. But look at the point where that tangent line would have to exist. We see that it's not continuous there, it's not defined, therefore it's not differentiable there. Remember, one of the conditions for differentiability is that it must be defined and continuous at that point. Okay, so there's no tangent line here because it's not differentiable there. Okay, no tangent line. All right, well, what about the next one? Well, we've got a secant line that looks like it's horizontal, and I would think to try to draw a tangent line right around there, but again, that's not possible because the only place where I could draw a tangent line, I see that it's not differentiable there. So no tangent line, again, because it's not differentiable there. And again, we saw this in a previous lesson. Why isn't it differentiable there? Well, because the slope of the tangent line as we approach from the left is not equal to the slope of the tangent line as we approach from the right. Well, you can see where we're going with this next one. Again, we see no tangent line for number 4. Again, the only possible place here, well, actually there is no place in general where there would be a tangent line that's parallel here. Now, let's look at number 5 now. Well, we've got a couple places where potentially that tangent line would be parallel. A couple places here. I think I got all of them. Right? So I'm able to draw 3 different tangent lines there that are parallel to the secant line that you see listed. And for this next one, let's see if we can do a few others. Looks like we can do one right around there, one right around there, here, here, and here. And I think those are all the ones. So we've done about 6 of these now. We've seen 3 of them where we couldn't draw a tangent line and 3 where we could. What criteria do you seem to think there is that will allow us to have a tangent line between the endpoints of the secant line that has an equivalent slope? And the overriding criteria that we seem to have is that there must be, first off, one, the function must be continuous. And then also, it must be differentiable. The function must be differentiable. And you could have actually just straight up said that the function must be differentiable because by definition, if a function is differentiable, then it must be continuous. So we can then say the following. Based on kind of our exploration, we're able to start drawing some ideas. We can say the following. If a function is continuous on the closed interval and differentiable on the open interval, there must exist at least one x value, which we'll call c, such that our f prime of c, or what we call our instantaneous rate of change, which gives us the slope of the tangent line in these previous problems, is equal to, if we see here, the average rate of change. The average rate of change, which gives us the slope of the secant line. So informally, when I'm trying to describe the idea and the concept behind the mean value theorem, I kind of describe it as such. Suppose you were going on a road trip and you were driving for 1 hour. So let's say you were driving for 1 hour. And during that hour, after that hour, you look down at your car speedometer or your car's info, and it tells you that suppose you averaged 60 miles per hour during your road trip. What the mean value theorem is saying is, assuming that your trip was continuous, right, that you were driving constantly, and you averaged 60 miles per hour, that means at some point during that 1 hour road trip, you had to have driven for at least one instant 60 miles per hour. Now, maybe most of the time you were driving closer to 50 miles per hour, and some other time you were driving closer to 70 miles per hour, but it makes complete sense that if you were averaging 60 miles per hour, that at some point you had to drive 60 miles per hour. So if you go below 60, in order for you to have an average of 60, you'd have to have gone above 60, in which case your speed at some point would have been 60 miles per hour. And that's effectively what the mean value theorem is saying. That's the idea behind it. Now let's put this theorem into practice with a couple of different functions and just to see whether or not the mean value theorem applies. And if it does, let's find the c values that lie within that given interval such that it's true. So we did some problems that were somewhat similar when we were talking about the intermediate value theorem. So let's look at number 8. Let me zoom in on this and just kind of work with this on number 8. So first off, let's look at this function and let's look at the interval and let's ask ourselves whether or not first the mean value theorem applies. And the answer is yes. The mean value theorem applies. And let's make sure we understand why and write down why. Because f of x is continuous. It's continuous on the closed interval -3, 2, and differentiable on the open interval -3, 2. Okay? We see that it's a polynomial function, therefore it's always continuous, and therefore its derivative is also going to be continuous. Its derivative would exist, therefore it's differentiable on this interval. So now that we know that the mean value theorem applies, we want to find the x value that's in this interval, which we'll call c. We want to find the c value in this interval such that the instantaneous rate of change is equal to the average rate of change. So let's find both. First off, what is the instantaneous rate of change? Well, the instantaneous rate of change is the derivative, f prime of x, which in this case, using the power rule, simply is 2x minus 2. Now let's find the average rate of change, which is just what we think of as our slope. So we're going to use the endpoints of our interval, so f of 2 minus f of -3, all of that over 2 minus 3. If we break that down, what do we see here? This would be 3 minus 18. So f of 2, if we plug that in, is 3. F of -3 is 18. All of that over, oops, I made a mistake down in the denominator. I apologize. Sorry for the confusion. It's 2 minus -3. The endpoint was -3. So this is going to be 5. So -15 over 5 is equal to +3. Okay? So I'm going to make this a little bit smaller here just so we have some space to work with and move this up. Okay. So now what we want to do, and let me actually switch colors so to kind of distinguish it a bit. We want to find what is the C value such that our instantaneous rate of change is equal to our average rate of change. Since we're solving for C, I'm going to replace my x's with a C. So 2C minus 2, that was our instantaneous rate of change, our derivative. And let's write down our average rate of change, which we said was, in this case, did I say, this should have been -3, I apologize. This should have been -3. Sorry about that. -15/5 should be -3. So now let's finish solving for C, and that's going to be -1, and then C is equal to -1/2. So this is the x value. This is the x value in this interval between -3 and 2, such that the slope of the tangent line is equal to the slope of our secant line, or where our instantaneous rate of change is equal to our average rate of change. Okay? All right, let's try a slightly different problem now. Or actually pretty similar problem, but let's maybe do this with a trigonometric function. So first off, let's ask ourselves, is this function one in which the mean value theorem applies? And the answer is yes. MVT applies because it is continuous on our closed interval, pi over 2 to 3 pi over 2. How do we know it's continuous? Well, look at the function. It's cosine. We know cosine is always continuous. And differentiable on that open interval. Okay, so now that we know MVT applies, there's going to be a C value somewhere here in this interval such that the derivative of cosine is equal to the average rate of change. Okay, so let's find the derivative of cosine. F prime of x is equal to negative sine of x. Okay, so this is our our instantaneous rate of change. The slope of our this is the function that gives us the slope of our tangent line. Now let's find our average rate of change. So just traditional slope, we're going to say f of 3 pi over 2 minus f of pi over 2. All of this over 3 pi over 2 minus pi over 2. Well, this is going to be, if you think about your trig functions, this would be 0 minus 0, all of that over pi, which is just 0. So now what we can do is we can set our instantaneous rate of change and our average rate of change equal to each other. So we can say negative sine of C is equal to 0 because we're solving for C. And we're trying to figure out what C is such that negative sine of C gives us 0. Well, that happens at 0 and at pi. Now, which of these would work? Well, think about it. Which of these values are in this interval here? And the answer is just pi. So we would disregard 0 because it's not in the interval, And so our C value would be equal to pi. So that is the x value within this interval such that our slope of our tangent line is equal to the slope of our secant line, where our instantaneous rate of change is equal to our average rate of change.